Yeah, we are commencing. Okay. Okay, so with a slight technical delay, we start the afternoon session. Our first speaker in the afternoon session is Eszter Békési, who obtained her PhD degree at the Utrecht University and after continued her career in our institute, and she's a great promise for the future in the geothermal domain. So Eszter, please give your talk.
Okay, so hello everyone. In this afternoon, I'm going to give this presentation about the stress field in the Pannonian basin and its adjacent areas. So for the afternoon, we will move to the Pannonian basin. I think the rest of the talks will focus mainly on that. So the Pannonian basin is a Miocene Beckard basin in Central Eastern Europe that was formed in response to subduction in the Carpathian. So the active steam-drift phase migrated in time and space, but it completely ended by about 9 MA. So this active drifting phase was followed by thermal subsidence due to positive cooling, and also neotectonic inversion initiated. These processes are still both active these days. So before I start concentrating on the stress field of the area, I would like to mention a very important project, which is called Creating and Analyzing the Seismotectonic Model of Hungary. So in the framework of this recent project, very nice new results on the lithospheric structure and active geodynamic processes took place, which can be later used as a basis of new studies. So this project was basically a consortium between the GeoMega Ltd and the Institute of Earth Physics and Space Science for the memory of the well-known Frank Horvath. So I will just show you some slides with some interesting results, not all of them. One important aspect were the seismological studies. Here you see new Conrad and Moho depth maps based on receiver function analysis. Later on, Daniel Kalmar will talk also about this a little bit more. Also, a nice outcome of the seismological studies are these 3D S-wave velocity structure images, which are available from far beyond the Pannonian basin from different depth intervals. The study is still in preparation or submitted, but soon will be available, hopefully. Here we also have a new focal mechanism solutions from inside and all around the Pannonian region. Based on those focal mechanism solutions, we managed to produce a new stress study. And also we had availability to new dense GNSS network, which facilitated the study in more detail on the strain field of the region. Additionally, a new seismic catalog was produced, which is revised and available for the wider region as well. And then, based on very dense active seismic data and also well data, a very detailed neotectonic map was produced. Unfortunately, it's only available for Hungary, but it's something that can be applied also for geo-energy applications in the future. And based on many of these results, one of the major outcomes of this study is the new seismotectonic map of Hungary, which can, of course, be extended for the wider region as well. So now going back to the stress in the Pannonian region, the latest studies focusing on this region were produced about 15 to 20 years ago, corresponding to Bada et al. So in the left, you can see the direction of maximum horizontal stresses in the sphere, with the observations shown with different colors and the interpolated field in the back with gray. So what you see is that this very striking northeast southwest orientation in the middle of the Pannonian basin, which was explained by the movement of the Adriatic microplate towards the north and its counterclockwise rotation, as shown by this velocity mapping here. So in this study, not only the direction of horizontal stresses, but also the stress type, the so-called relative stress magnitudes were studied based on focal mechanism solutions. And what you can see here is that almost the entire Pannonian basin is under strike-slip stresses, and there are even some regions marked by normal faulting, which is very interesting. So this study was really nice, but it was often based on relatively sparse data sets. It also included some unreliable stress indicators. So our goal was to revise this database, also add many new information and measurements in order to produce a more reliable database which can be used for the tectonic implications and also for geo-energy studies, at least until the level. So the most important basis of this new stress study was the new focal mechanism solutions. To actually calculate the focal mechanism of these events was facilitated by the very dense seismic network, which corresponds to the Alp Array project. So here in the middle, you see our solutions, which are available also for relatively small magnitude events. And we also collected the solutions of international agencies from all around the peripheral parts of the basin. So in addition to these FMS data, we also collected so-called borehole breakouts from different already available databases from Bada et al. And also from the world stress map. So the focal mechanism solution and these breakouts represent the main stress indicators for the regions shown with red and with blue in this map. What are borehole breakouts? These are basically from wells, and these are formed due to stress concentrations on the wellbore, and they open up in the direction of SH mean, so the minimal horizontal stress. So altogether, we revised all these new and already existing data, and we assigned the quality groups to them according to the world stress map. We only considered A to C quality indicators, which means that the largest uncertainty assigned to a single measurement is 25 degrees. Also, what's important to note is that compared to the previous database, we have almost doubled the available indicators, which facilitates the much more detailed analysis of the stress field. In order to also infer for the stress state where indicators were not available, we interpolated these orientations on a regular grid. For that, we used a cluster-based methodology. Basically, we managed to retrieve these orientations for almost the entire study area. So the background color shows the uncertainty of these interpolated orientations, which, as you see, are almost everywhere below 30 degrees. We made sure that on the basis of the regional trends, we also keep these local anomalies in the stress field. So what we can see if we look to the orientations, that the inner part of the Pannonian basin is marked by northeast, southwest direction. But if we go to the southwestern part of the study area in the Dinarids, and also in the north, east-west north-south orientations become dominant. And then if we move towards the eastern and the southern Carpathian, the stress field kind of rotates to east-west, and it even rotates back in the southern Carpathian towards northeast. One interesting anomaly that we saw in this interpolated stress field is located here in the western border of Hungary, where there is quite a large anomaly with east-west oriented stress field present. So the focal magnetic solutions also allow us to infer for tectonic regimes, so the style, tectonic style or the type of the stress field. In this map, with red, you can see normal faulting regime, where the largest principal stress is vertical. And then in case of the strike slip marked with green and the reverse faulting regime, the largest principal stress corresponds to stage max, which is basically true for almost the entire study area. So you see that in the Pannonian basin, mostly strike slip to transpression are dominant. In the Alps, the Dinarids and the Pannonian basin transition zone, so basically here, reverse faulting becomes more and more important. Normal faulting is only observed locally here in the southern Carpathian, and there's a small anomaly in the north, but it's only based on one focal magnetic solution, so I wouldn't really trust it that much. So if we move further, based on these interpolated stress orientations, we calculated stress trajectories. So basically, these lines with gray represent the orientation of the maximum horizontal stress here. These trajectories and the background tectonic regime map were compared to neotectonically active structures. All in all, we can say that they show very good agreement in many locations. For instance, the sinister structures in the Eastern Alps and along the mid-Hungarian mobile belt, also the textile structures in the Dinarids fit well both with the trajectories and also with the type of the stress field. But there are also some examples for suboptimal fit. One very interesting is here, these dextra structures. It's located at the location of this anomaly that I mentioned before, this east-west trending stage max anomaly, where we cannot really explain the activation of or reactivation of these spots with the current stress field. Also, an example for that is the extensional structures here in the northeastern part of Hungary, where we observe or infer for reverse faulting regime. What's also very interesting to mention that it has previously been proposed that the regional stress pattern is locally influenced by the topography. So it means that basically topographic heights exert some additional compressional stresses towards basins. And actually our results really supported this hypothesis, for instance, in case of the Styrian basin and also some parts of the Pannonian basin, which are both marked by these compressional anomalies in the stress field. We also compared to our stage max orientation with seismic anisotropy studies from DeepL, down from the mantle. And what we've observed is that for the majority of the study area, the direction of the fast axis corresponds to the direction of SH min, so the minimal principal horizontal stress. And this anomaly that I mentioned before is also present in this map. And here, the stage max orientations align with the fast axis. Actually, first we would need to understand what's going on in the upper crust represented by our stress analysis in order to link it to deeper processes. But if somebody has an idea what it can be caused by, then we are really happy for any comments on that. So going further, now I talked about the tectonic implications, but there are also some geo-energy applications. For instance, for wellbore stability and also for the reopening of the fractures, which can be really important for instance, the enhancement of production rates. So in case of wellbore stability, we have dominantly stress-tip to reverse faulting regimes. And in this kind of stress rate, wells which are deviated towards stage max are considered to be the most stable. In case of the reopening of the fractures, it's really hard to tell which orientation is preferred because it can largely vary whether we have a strike slip or a thrust faulting regime. On the right, we can see a depth profile with measurements on the principal stresses. And you can see that the minimal principal stresses are very, and the vertical stresses are very close to each other. So it's really hard, there's a smooth transition between strike-slip to reverse faulting regime. That's why it's really important to assess in case of geo-energy application the natural state of stress locally. And also, you know, we have information about the stress regimes from earthquake focal mechanism solutions, which are mostly present in the Pannonian basin between about 5 to 15 kilometer depth. So in the lower part of the upper crust. But if you think of geo-energy applications, we have to go, of course, mostly shallower. So that's why it's also very important to consider the local effects and try to build local for instance, geomechanical models, which can also help with induced seismicity studies later on. So until now, I talked about the natural state of stress. Of course, based on our analysis, we cannot tell the absolute stress magnitudes, only the relative one. But still, if we disturb the natural state of stress, then the effective stress will change. For instance, any kind of mining activities like the production of hydrocarbons or geothermal energy, also subsurface storage activities or reinjection activities, basically result in the extraction or addition of fluids to the subsurface. In case of a fully saturated porous media, the behavior of reservoir rock is determined by the effective stress, which is essentially the difference between total stress and the pore pressure multiplied by this Willis coefficient. So what happens if we produce from the subsurface? Then we take out material and the pore pressure would decrease, shifting this small circle more towards larger effective stresses and kind of stabilizes faults. Actually, when we re-inject, then we increase the pore pressures, which means that our circle moves towards the failure envelope, which can cause induced seismic events. So if we decrease pore pressures, what can happen is that reservoir rocks or its surroundings compact. And it can also result in land subsidence that we often observe in many cases worldwide. And in case of induced seismicity, it's also really important to mention that not only injection activities can cause them. For instance, in case of Groningen, depletion-induced earthquakes are very important, and they can happen because the changes in pore pressure can have a different effect on the different components of the principal stresses, which can result in the enlargement of these small circles, then touching the failure envelopes. It's also an interesting point to mention that thermal stresses can also induce seismicity, but right now it's not the topic of this talk, so I won't go into details on that. So here I'm going to show you an example about reservoir depletion, pore pressure decrease, and then later on natural pore pressure recovery from a geothermal area in southeast Hungary. It's important to mention that here the pore pressure recovery was not because of re-injection, but much more like a natural process due to natural recharge. So it was relatively slow. So what we observe here, which is actually a regional phenomena in the Great Hungarian Plain of the Pannonian Basin, is that starting from active large-scale production from the 70s, the pore pressures and, of course, groundwater levels started to decrease, which was accompanied by large amounts of compaction and land subsidence, which are both documented in earlier studies. So later on, as you see from the 90s, the recovery of pore pressures occurred in this region. And in relation to that pore pressure recovery, we could map surface uplift of the area. We mapped it using satellite data for the period of about 4 years. So basically, the compaction of the reservoir occurred in here. And if we go further, we set up inverse models for ground deformation to understand what's going on the subsurface and to estimate some very basic properties of the reservoir. So what we did is that we assumed the reservoir to be like a disc-shaped geometry that is undergoing a uniform pressure increase in this case. And among different parameters, we also estimated the decompaction coefficient of the reservoir. It's important to mention that this decompaction coefficient can be associated with the elastic deformation of the reservoir. So based on that, we got different values depending on what kind of reservoir height we assumed, of course. But in all cases, even if we assumed a very thin reservoir, we got quite low values for the decompaction coefficient. So actually, as for a compaction coefficient of these types of reservoir rocks, these silicic-clastic sandstones, then we had to assume that some other type of deformation process must have had a role as well earlier in the depletion period. What we learned from this case that we are almost sure that the viscose, so permanent deformation of the reservoir also occurred back then in the past. And actually, if we look into examples worldwide, it's very well known that the contribution of viscose deformation is important in case of reservoir depletion. For instance, in case of the Groningen gas field, both laboratory tests and also compaction models calibrated with surface movements showed that these viscous deformation have very strong effect. So what's important in here is that in case of these applications, first, it would be very important to understand how reservoir rocks basically behave due to pore pressure changes. And it would only be possible with very small scale coupled hydraulic and mechanical models. Actually, these models could also help in understanding what happens if we re-inject into these reservoirs, because there are problems now that these reinjection activities into these Miocene sandstones here, which form the most important reservoir rocks in the region, are quite unsuccessful. So it can also be a way to move forward. So now I will conclude because I don't think I have more time left. So going back to the large-scale stress field study, we can say that we reconstructed the stress field in the Pannonian Basin, and our results basically agree very well with earlier ones, but they provide a much more detailed picture, and I find them much more reliable so they can be used for further tectonic or geodynamic studies also. So what we see is that the main control is still the motion of Adria, but it's also important to note that the basin has this land of position from the east. Therefore, we have transpressional stresses acting in the majority of the Pannonian basin. It's also important to mention that we see complete lack of extension, which is basically different from what we knew previously, at least about a few regions of the Pannonian basin. Further large-scale tectonic or geodynamic implications can be drawn with the joint interpretation of the stress field and the new geodetic strain analysis, which will be presented later on with Kristóf. And about the geo-energy applications, our results can be served as first-order boundary conditions, but of course, local studies are really crucial to the planning of these very important and sometimes risky activities. Also, as I said, a way forward would be to understand how exactly rocks, reservoir rocks deform in response to pore pressure changes, which could be done with coupled hydromechanical modeling in small scale. So that was it. Thank you very much.
I want to turn to the on-site audience whether there is any question. Let's see.
Thanks for a very interesting presentation. Important topic, not only for geodynamics, as you mentioned, but also, as you mentioned, for geo-energy. Could we go back to this map where you show the, this one, the regime? Basically, the blue area in the Ukrainian Carpathians, how well is that constrained? That's one question. And I have a question also on the Styrian basin, which also, as you mentioned, reverse faulting. It's also an area underlain by very hot upper mantle, and an area where basically we have the evidence for very recent uplift, which we have interpreted in the past as a result of the compression. And I understand from you that you turn it around. You say, well, the topography is leading to compression, but actually we know from areas like the southern Scandies that in the area that has topography, that we have extension, and the surrounding area has compression. So how does that work for the Styrian basin?
Yeah, well, I didn't really go that much into this topic. I just saw this kind of interesting idea of Bada et al. And I saw that, oh yeah, it could work in here because that's what we observe. But yeah, well, I have to get into more details on that. I cannot really.
I think it's a very interesting question whether the topography is the result of the compression or vice versa.
Yeah.
And coming back to the Ukrainian and Carpathians.
Oh yeah, yeah. So as you see here, I went to this slide because here you see actually the focal mechanism solution where we have them as these colored dots. And you see we only have one observation from here. So it's not really well constrained. And the sizes, of course, it depends on the interpolation methodology. So, you know, it's like, that's why I don't really comment on the extent of that. Because
in all the maps, also in the previous maps, this area comes out as a very anomalous, and I was just wondering.
Yeah, actually, I looked into that solution. We looked into that solution with Zoltán Weber, who did the calculations from the inside of the basin, and we found it quite reliable for interpretation. So we just left it in the database.
Okay, thanks.
Is there any more question from the audience? I know.
Maybe working. Okay. Maybe it will be a sort of philosophical comment. Okay? If you go back to this previous map, but Sil suggested equally, and I fully agree with Sil. In that sense that this Styrian uplift and the stress that you can deduce from different markers, they need an explanation. It is not so easy. And I discussed a lot with the Austrian colleagues, and they only see normal faults, only see extensional features in the surface. And then in the deeper crust, or let's say middle crust, we do see a difference. Okay, so I think that my comment is that we have this is an excellent work, and I think the excellent because it shows us the next direction. We have to understand the coupling or decoupling, the surface deformation or near surface deformation, and the deformation in deeper crust and even in the mantle level. This is my absolutely convinced, because there are so many problems with the fault kinematics what we observed, and the stress indications what you can deduce, that we have to work on that line. I think this is absolutely a must in the near future, because we despite this fantastic advancement, in my view, I do see the problems, maybe because I'm structural geologist, but I do see quite a number of problems. I'm not speaking about this Western Hungarian anomaly where we put extra instead of putting reverse fault on a sigma-1 perpendicular structures, and this is the same for the Moore fault, where the kinematics seem to be normal, and although despite it's almost perpendicular to the sigma-1. So I think that it is extremely good. And then I'm very excited to go on, because this is how we will understand how this part of the world is working.
Yeah.
Okay, so sorry for this philosophy.
No, it's fine. And actually, I would add to that only that actually I looked into some of these borehole images, and you see a large amount of rotations in the stress field, even in an interval of 1-2 kilometers. So it's extremely interesting. So what this map represents, of course, is the deeper part, and what we see on the surface can be completely different, as you also suggested. Also here, close to Vienna, it's completely different in a shallower, or it's different in a shallower level. So.
One more short comment, then the timing. This is equally important, in my view, was what Balázs Koroknai and all the other people did as a sort of neotectonic map. The problem is the timing. And what is the timing for that? It is, of course, it is recent.
Yeah.
How long, when it was established? Because if I look to the Neotectonic map and to this map, there are discrepancies, quite important discrepancies. So maybe my suggestion that we have a new area. This is maybe a new stress field, a new deformation pattern, which is quite young, very young. And maybe even quartering. And the Neotectonic map is not necessarily reflect the quartering.
Yeah, sure, of course, it can be much.
So the Neotectonic map will not be Neotectonic in that sense.
That's true, yeah.
Just a quick one about this Ukrainian big anomaly. I think we could work on that, knowing some guys at UG after that.
Yeah.
My gut feel, just like Ziad commented earlier, is going to go away probably once we have more data to plug it in. And about the Styrian basins, is coming from Austria, kind of. So is that it's not. I would reposition that label of Styrian basins a little bit further to the northeast. Yeah. It doesn't do justice to the Styrian basin where the label is. And it's a small detail, but you see the Lavantal fault cutting across this thing.
Oh yeah.
So, okay. So mentally you have to push it into the area which read the textbook, which is the shall we say the background strike-sleepy stress field, which we see all over the place. Where you have this anomalies really along tracking the border with Slovenia. So it's a different domain going into the Karavanka and all that jazz. So that has its own life. So I think even the Styrian basin read your textbook, if you will, because it's so good.
Fine. Thank you.
Thomas, just to involve the more junior generation as well, and the online participants can think about questions.
Okay, thank you. It was a very nice presentation. When you showed the evolution of the reservoir, you showed an equation which, this one,
It's a very simple one.
I know, that's why I want to ask if, in these studies also consider the dissolution precipitation processes as well.
No, it's purely poroelastic.
Yeah, because, when
Of
you,
course, then,
yeah, because when you have precipitation, you have a lot of
Yeah.
focal points, where
Yeah.
that also helps to support, this whole.
Actually, I planned a
So-
slide on that, but then it became too long. But also going back to these injection issues that I mentioned, this component of mineral precipitation, also microbial activity, were found to be very important addition to the understanding of what can go wrong, and it should also be considered. And it's actually very, very well studied from a group of the Utrecht University. So
Okay, thank
it's
you.
interesting as well. Yeah.
Okay, thanks.
Thanks. Okay, we just need to check whether we have any message in the chat window. Oh, yeah. Just need to somehow close this. Yeah. Okay, and I ask the online participants to just to click here. I think it's going to work. Okay, I see no question. Okay, then thank you very much, Eszter, for the nice presentation, which fits pretty well into the topic of this seminar. And now I ask Kristóf Porkoláb to come forward. Kristóf also did his PhD at the Utrecht University, and he's a kind of a polyhistorian in geology, doing a lot of different things. And now he will talk about the stress regime and deformation in the Pannonian basin. So, Kristóf, please. Oh, yeah, of course.
Thank you very much. Okay, hello everyone. I'm Kristóf, and I will follow up. Eszter spoke with, actually a similar topic. I will also stay in the Circum-Pannonian region, and I will also focus on neotectonics and active tectonics, but I will focus on a new study that concerns the GNSS-derived strain rates for the same region. And it was part of the same project, so the seismotectonic project in the Pannonian basin. First, just a quick recap. I mean, Eszter told about most of this, but we are still in the Pannonian basin, and I just want to show that this is what we previously knew about the geodynamics of the region. So there is the Adriatic microcontinent that is moving towards the north, and this Pannonian basin is in a position that it's surrounded by the Alps, the Carpathian chain, the Dinarese chain. So it's in a frame of mountains. It has nowhere to go, so it undergoes some shortening. And I would also like to highlight these plus and minus signs, which denote the vertical motions of the region. And these plus and minus signs are based on geomorphological, geological observations. So we see Trans-Danubian range moving up, Carpathians, on most places the Carpathian chain is moving up, but the center of the basin is under subsidence. And the structure of the basin is actually quite well mapped by now, and here is the map by Koroknai et al. And Volum et al. From just a couple of years ago, and there is a really high resolution of structures that can potentially be active or are considered to be neotectonically active, so active in the past couple of millions of years. So we know already a lot about the structure, but still quantitative deformation or strain rates for the region were not calculated yet. And this is the previous GNSS velocity interpolation for the region by Granertzi et al. 2005. And we can see that this motion, the general motion of Adria, is very well resolved by this work, but you can also see that the GNSS stations were were not exactly dense at the time of this interpolation. So the interpolation didn't exactly allow the resolution of the strain rate field properly. So there is things to improve in this matter, and our goal was also to use a much denser GNSS database that we have now for a new interpolation and also derive the strain rates for the region. Okay, so this is the new data set, and actually the work was just published 1 or 2 weeks ago. So you can check the article for details, but I will actually tell you most of the details now. So this is the data set that we used. You can see we have a lot of stations now, thanks to an integration of European GNSS stations. Already just the raw data tells us some important things, how the Dinarids is moving towards the north-northeast, and also, interestingly, how the eastern and southeastern regions move the opposite way, actually, with respect to a fixed Eurasia, I should add that. Okay, for the interpolation, we did it by a method called ordinary kriging, which is a stochastic interpolation method, and it's using the uncertainty of the GNSS measurements as a weight factor in the interpolation. And it is, as we know, it's very important always for tectonic purposes to smooth the velocity field. There are different ways of smoothing the velocity field. The way we did it was scaling the uncertainty that then go into the kriging equation. If we don't smooth the velocity field, we get this checkboard pattern. So you have this average or this typical interstation distance, and then the dilatation rate, which shows you areas under extension or shortening. They just switch between stations. So, but then when we apply smoothing, we get a much smoother picture, of course. And but we also tested different uncertainty scaling levels to determine the ideal level of smoothing. And here we can see that this 1 millimeter per year minimum uncertainty is a very good way of removing the small wavelength noise, but preserving the long wavelength, so tectonically important signal. So that is what we chose for the interpolation. And this is the product of the interpolation. I mean, the colors and show in millimeter per year the velocities relative to Eurasia. And the blue arrows show the original data, and the black ones are the interpolated values. So we see values of exceeding 3 millimeters a year in the Dinarids, moving towards north-northeast. That decreases a lot and quite quickly when we enter the Hungarian part of the Pannonian basin. We still have a millimeter per year motion around here, but then we go to 0.1, 0.2 towards the central Hungary. And then there is a 1.1, 1.5 millimeter per year southwestern motion in the Romanian areas. Okay, from the velocities calculated the magnitude of the strain rate, and this is the scale here is 10 on the power of -8. So 2 here is 20 nanostrain per year, and this 20 nanostrain per year is reached in the Dinarids and in the southwestern part of the Pannonian basin. And then this again diminishes towards the Pannonian basin. And here the red arrows and the perpendicular black arrows show the principal strain rate. The red ones are shortening and the black ones are perpendicular extension. So we can also already see, but I will get back to this later on. Also, it's important to observe that at the region of the Trans-Danubian range and the North Hungarian range and the Western Carpathians, the strain rate magnitude is quite close to zero, actually quite close to negligible. Barely any deformation is happening there. Okay, dilatation rate shows regions that are under shortening with negative dilatation, so the blue colors, and then green where the areas are getting larger, so there is extensional type of deformation happening. It's interesting to see this part in the dinarids, which first I thought could be the result of not having any GNSS stations in the Adriatic Sea, but actually when we check closer, there are some stations at the shore of the sea, and there are some stations more towards the higher mountains, and those are just simply going faster towards the northeast. So there is some real extension going on here, probably. I will just quickly show the rotation rates. So red colors are the counterclockwise rotations, and blue colors are the clockwise rotations. So there are some counterclockwise rotations going on in this corner, and also here in the Carpathians, and in a slower manner in the Eastern Alps and Western Carpathians. And inside Hungary and inside it's relatively minor, so very close to zero, like -1 nanoradian or +1 nanoradian a year. It's really quite low. Okay, so here is the deformation type. Blue colors denote shortening, these pinkish colors extension, and then in between this greenish shows the shear type deformation. Again, what we see is, and of course the principal strain symbols are also there, and they are also proportional to the strain rate magnitude. So larger symbols mean faster strain rates. And so we can see that there is a transpressional type deformation in the dinarids and also in the southwestern Pannonian basin. And then when we go in central Hungary, we have almost pure shortening. And in the eastern boundary of the Pannonian basin, this region is characterized by shear type deformation, where shortening and perpendicular extension is quite well balanced. And we have regional extension in the Carpathian region. The main extension direction is, northeast, southwest, or northeast, southwest. Okay, I'll just say a couple of things about implications of these horizontal strain rates for active tectonics. So what we see from the geodetic strain rates, this transpressional type deformation in the dinarids and the transition or the junction area of the dinarids, Eastern Alps and Pannonian basin, these fit very well to neotectonic structures that we see in this region. So these dextral transpressional faults in the dinarids, for instance, fit quite well to this. What we also see is generally a shortening in the Central Pannonian basin, of course, a very slow shortening, and a slow shearing along the eastern boundary of the Pannonian basin. Okay, so there is in most cases, quite a good fit, but also there are some problems that I would like to discuss now. And this also brings us back to the debate of the previous talk, at the end of the previous talk. So let's start with pure shortening in Central Pannonian. Okay, so this is the area of mid-Hungarian mobile belt, which should be a sinistral strike slip structure in the neotectonic phase. Now here, there is almost no perpendicular extension in the geodetic strain rate. It's a pure shortening. And to make this even worse, this shortening turns parallel with the faults towards the east, which is not what you would expect in a strike slip deformation zone. The shortening should be north, east, southwest. So it should be oriented something like this to fit with the observed structures. Okay, so how could we explain this? I mean, first, but also I think Laci proposed at the end of Eszter's talk, maybe the deformation that caused these structures is simply not there anymore. It changed slightly. So maybe deformation changed with respect to the neotectonic phase. So current deformation does not equal neotectonic deformation. That's the first possibility. And or deformation is accommodated by processes that are not reflected in these structural maps. Okay, maybe lithospheric-scale folding, aseismic creep, something that we don't see that are not part of this map, but they are there. We just have to quantify it somehow and understand how it works. Just to compare with seismicity, and this actually also helps with this discussion, I think. So this is the new map that Jury and Barbicets and others made for the seismotectonic project now. And what we see is that most of the seismicity within Hungary is located in this region, in the Trans-Danubian range, North Hungarian range, in this region. And actually, this is the slowest deforming region based on the geodetic strain rates, right? And the southwestern Pannonian basin deforms actually quite quickly, geodetically speaking. And well, we have a lot of earthquake in the Dinarids and in the transition area, but if we go south from the Balaton or west from the Balaton, in this region, we still have a slightly higher strain rates, but we don't have a lot of earthquakes. So that also, again, tells us that maybe a large portion of the deformation is aseismic. It's not related to earthquakes and slip on, or at least discrete slip on faults. Okay, this is just to show again this new seismotectonic map, which integrates all the work of the project, or most of the work of the project. And I'll just highlight, okay, we have the neotectonic faults from the neotectonic fault map, but here active, probably active, and potentially active faults are distinguished based on their correlation with seismicity, based on the faults themselves displacing any quaternary or not. And also, we can compare it with the stress trajectories produced by Eszter, these blue lines. And with the black and white symbols, we have the strain rate, principal strain rate axis. And well, I just see that you can barely see it on this wall, but there are some white contours, which are the strain rate magnitude contours, but they are not really visible now. Okay, so this was the horizontal part of the talk, and now I will move to a vertical direction. Okay, so this is the vertical component of the velocity, and just the data. Already looking at this, we can see a lot of arrows pointing down. So most of the area is under subsidence, and of course we interpolated this data to get a more complete picture. And this is a red and blue color scale, but we barely have any red on the map because most of the area is under subsidence. We have some very close to zero values, maybe a little bit uplifting values in the region of the Trans-Danubian range, in the Carpathians, but most of the area is under subsidence. I will just leave it at this point. I will just leave it like this, and I will move back to what we see when we look at all the literature and ask the question, what does quaternary geology tell us about uplift and subsidence patterns in the Pannonian region? So first observation, that quaternary sediment thickness is quite irregular. So there are some uplifted regions which can be recognized based on simple geomorphological geological observations. There are late Miocene, Pliocene strata that are eroded in elevated positions. So there must be some regions that experienced uplift throughout the quaternary. Okay, a very important source of data is terraces and travertine horizons along the Danube. This constrains uplifts of the Trans-Danubian range during the Pliocene and Quaternary. This is very nicely summarized in this particular paper, for example. There is also uplift recorded in the Eastern Alps, in the Carpathian chain, and Of course, yes, we also have subsiding regions. So in the central Pannonian, several hundred meters of quaternary sediments accumulated in the depot center. So we also have places of subsidence. This is summarized by this section here, which I think is a figure of Horvath and Kluting, 1996. So we have uplifted regions, the central, so this color actually is the quaternary. So we have in the central Pannonian subsidence and accumulation of quaternary sediments, and then uplift on the other flank as well. The question was like, why does this happen? And what can be the explanation? And Horvath and Kluting and further papers elaborated on that, came up with a very elegant solution. This shows predicted stratigraphy with some late-stage compression in the model, and that shows that the stress-induced deflection can explain such patterns of uplifting basin margins and subsiding basin centers. And this can happen because we still have a continuous northward push from Adria, but the Pannonian basin cannot move anymore towards the east. Okay, but when what we observe now, based on the geodetic data, is that most of the things are going down. So how can we explain this discrepancy between geomorphological, geological observations and geodetic data of present day? So to the right, we have the same figure, but we centered the color scale at the mean vertical uplift, which is very close to -1 millimeter per year. So this actually shows the relative uplifts quite well. And what we see in the relative uplift is the subsidence of the basin center and the uplift of the basin margins, Trans-Columbian Range, Apuseni Mountains, Carpathians, all around. And the plus and minus signs are geomorphological, geological observations independent from the geodetic data. So when we look at this figure, we see plus signs where we have red color, so relative uplift, and minus signs where we have relative subsidence. So what I think we can conclude that the relative geodetic motions correspond well to the geological, geomorphological observations. But when we take this picture, the correspondence is not clear. So what could be the case is that we have a smaller wavelength signal, which is related to, this process, for instance. Okay, so the buckling of the lithosphere, and the smaller, okay, this is in good agreement with quaternary geological observations. But then there is a longer wavelength signal, which appeared to be a slow subsidence for large parts of mid-latitude Europe. Okay, so maybe there is a superposition of these two signals. And the question is, how can we explain this? Okay, so this seems to be a very regional subsidence. So can this be an effect of regional asthenospheric flow? According to some models and theories, it maybe could be explained. So this is a figure from a glacial isostatic adjustment, and precisely the millimeter per year vertical motion prediction from a glacial isostatic adjustment model, which shows that due to the melting of the Fennoscandian ice sheet, the large uplift of this region has to be accommodated by a slow subsidence of mid-latitude Europe, which could be like go up to, I don't really know how precise this model is, but it's in the order of -1 millimeter per year, which is actually exactly the long wavelength subsidence that we see here. Okay, so this could be a potential explanation why we have a long wavelength subsidence. But of course, many other things can also influence vertical motions, and this has been published and summarized already in many different papers. So there is basin scale asthenospheric deformation patterns that can be very important. There is the differential loading of the lithosphere related to sedimentation, and this can induce flow in the ductile crust, which can also be important. And there is also effects of the climate. So increased erosion rates also increase rates of the vertical motions and amplifies certain effects. So these are also probably factors that modify the vertical motion pattern. So we have the lithospheric-scale folding. Maybe we have this regional asthenospheric flow, maybe related to glacial isostatic adjustment. And then we have other factors, basin scale asthenospheric deformation, loading of the lithosphere, and climate effects to complicate the picture. So we have many different factors that can contribute to the observed vertical motion. And yeah, it would be really good to move forward and try to quantify some of these aspects, maybe with some coupled models, and determine the relative importance of these factors. And yeah, I will conclude with that. So yeah, I'll just read the points. So new interpolation of GNSS data provides important constraints for seismotectonic and geodynamic applications. The current deformation of the Pannonian is a northeast-southwest shortening, largely with a very much subordinate perpendicular extension. And this is still fits the picture that it's induced by the north-northeast ocean motion of Adria, but the opposite sense motion of the southeastern regions also seem to be important. The deformation is relatively slow compared to plate boundaries, but it's definitely not negligible. And there are some minor discrepancies between the current geodatic and the mapped neotectonic structures. So this raises some questions. Is there a difference between neotectonic and active deformation phases? Is deformation accommodated by aseismic deformation that is difficult to observe? And current vertical motions appear to be the product of different lithospheric asthenospheric processes acting on different wavelengths and timescales. Thank you for your attention.
Thank you, Kristóf. So the talk was mainly about subsidence, but it was very uplifting. And Sid immediately has a question or a comment on it.
Very, very interesting results and really a major step forward. Your conclusion, I think, makes a lot of sense. Also, in view of what we have learned from Iberia. Iberia, microcontinent, very high elevation, hot implemental. At the same time, lithospheric folding in the central and the western part, superimposed on the overall high topography. And what Cepoloni with his vertical GPS interpretation has shown is basically that superimposed on the ongoing shortening and folding of Iberia, you can clearly see the effect of a dying plume under Iberia, producing large-scale subsidence. And what you showed reminds me a little bit to that. Of course, Iberia, probably the vertical motions are larger because it's closer to the plate boundary. But I think this is a very interesting result because the Iberia story is also characterized by a succession of highs and lows. And there, the orientation of the highs and the basins in the center of Iberia is very much perpendicular to the orientation of the present-day compressional stress regime. So I think it's worthwhile to further explore this. The overall pattern, let's say, of downgoing in the Dinarids was actually a surprise to see that. For some of the other areas you might expect it, but not there. And that's interesting because that's the area where you show the largest horizontal motions. So that's also very intriguing.
Yeah, and if it wasn't reflected in the raw data, I would say that maybe the interpolation is wrong or something, but I mean, you can just look at the arrows and they are there. So yeah, we just have to we just have to accept that, there is subsidence and have to find a way to somehow explain how this works.
More question? Lottie, so you're raising your arm, just stretching your
Maybe it's partly common. Okay, I like it very much because we didn't speak to each other. Okay, so you arrived to a very similar conclusion, but I'm just suggesting right during this discussion. Okay, so that we have to take care very much on this neotectonic or active tectonics or recent tectonics whatsoever. Let's put two questions maybe. One thing is very good solution that when you have strain and you do not have earthquake, then you say it's creeping. What happened in central or north central Hungary when you have earthquakes? That means the seismogenic crust is resolving strain, but still on the surface measure, you do not see it. This is a more tricky task, I guess.
Yeah.
What is your solution for that? Because it doesn't seem to be easy for me.
Yeah, these are relatively small earthquakes, of course. So when, I mean, in terms of surface displacement, these translate to minimal motions. But yeah, I think it was also very nicely put in Laci-Lenkei's paper that actually the rheology explains quite well this distribution of seismicity in the crust. So this is a relatively cold region. This is the strongest part of the Pannonian lithosphere, so that's why you would have some earthquakes. But at the end, to geodetically observe these, I think that would be difficult. These are, the magnitudes are like 3 and 4, and then that can translate to a motion of, yeah, not even a millimeter on the surface. If it's, I don't know, yeah, we did some calculations on that at one point. Yeah. So yeah, simply if these are like depth of these are 10 kilometers and the magnitude is, let's say, 3, then you barely have any motion on the surface. So I think that, yeah, could be explained by that.
Because what's really shocking for me, Kristóf, is that Transylvania and southern part of Romania is going due south.
Yes.
What's the explanation for that? I cannot digest it.
Yeah, I think the only way to explain it, or the only way I can explain it, is the Hellenic trench retreat still. So that is what can provide space for anything moving southwards. So that is already the effect of the Hellenic trench. And there is I don't know any other way.
That means this is relatively recent that this effect arrived to the Carpathians, no? What do you think on the age of this? When did it start? Because in the Miocene, we should expect a different tectonic setting.
Yeah, I'm not sure. Maybe it was already affecting it. It's maybe just difficult to see in the geological record this effect. But if it has an effect now, it must have had an effect also in the Miocene, I would say. But maybe we just cannot see it.
Yeah, you're not going to have a vulnerable data set back from the Miocene, unfortunately. But your explanation, I mean, intuitively, we are very far from the Hellenic trench, but
yeah,
this is the only thing.
Yeah, I wouldn't expected it, but that's
yeah. Thank you.
So there is no more question. Just take a look if there is question from the online participants again. Okay, I see no question. Chongi, so you okay? So just a confirmation. Thank you very much, Kristóf, for the nice talk and the great discussion. And we are continuing the second session with Márta Berkesi, who is got her PhD from the Utrecht University, and she's well known for her work on fluid inclusions, and she organized many international conferences in Hungary, and she just recently obtained, let's say, the highest grants in Hungary in her age to Lendület grant. So we again congratulate Márti and for your group, and her group is working on the fluids in the lithosphere and from the asthenosphere up to the surface. So Márti, it's my pleasure to invite you to give your presentation.
Thank you, István. Okay, here we are. Thank you very much, István, and thank you very much for the opportunity to little bit drive you in the philosophy and the amazing world of fluids. A lot of had been discussed about fluids today, and I'm very happy to see that recently a lot of is being discussed overall. No matter where we go, by means of Earth's scientific problems, then more and more attention goes to fluids. And I really do agree with this, because my philosophy is that we have to understand the Earth-related processes in a holistic way, always considering the solid state processes together with the fluid state processes, because according to our experiences and according to our results, and not our, but others as well, to some extent, to some concentration, to some activity, fluids are always there, even in the mantle, even in the core. There are some ideas at least on it, but in the lithosphere, certainly. Okay, now I'd like to give an introduction about what people think recently on the lithospheric scale fluid transport. And I'm trying to give you two recent examples, actually case studies, one from a subduction zone and one from a continental rift setting. Okay, so as I just told you, the importance of fluid has long been recognized. We all know that it's important in plate tectonics, in promoting earthquakes to some extent. Of course, we do know how important they are in magmatic and ore forming processes. But now I'm not going to talk about the geohydrological cycle and the oceans, whatever. We all know that they are important. I'm going to give the focus on the high pressure fluids. Why? Let me quote Miller, a very nice paper of Miller who reviewed the importance of fluids in the geophysical approaches. So let's quote him. The hypothesis that high pressure fluids act as an important tectonic driver suggests the lithospheric deformation and the earthquake cycle is substantially controlled by the mechanical, chemical, and time-varying hydraulic behavior of high-pressure fluids trapped at depth. This is very important. And the question from Csaba to Alessio was important because he was talking about we were talking about the water that is being saturated with the rocks. It exists, do exist, but the compressibility of water is much more different than the compressibility of these kind of high pressure fluids. I'm talking about CO2, I'm talking about methane, some sulfur bearing species, and the nitrogen. And if the compressibility factor changes by orders of magnitude than the water does, then it means that the pressure will be enormously high, a local pressure when the fluid is being present together with solid state rocks. And again, the high pressure is important because this fluid doesn't want to be at such high pressure, but they are at the deeper part of the lithosphere. They want to be somehow released, okay? So they are tending to decrease its pressure. They are tending to move upward by its upward movement. So for a long-term hypothesis, at least to some geochemical theories and philosophies, was that, okay, there are some fluids originating from at the base of the lithosphere, a deeper part of the lithosphere, but they are staying there. They are not communicating to the surface processes or subsurface processes. But this is not the case. But so that we can understand these lithospheric scale fluid processes, then let's see how the distribution of, like, for example, carbon or any other fluid molecule building element can be seen in a vertical scale, and then we go to the horizontal scale as well. We can see different, what is the point of this one? Different spheres, and of course we see, and this is what we expect, the heterogeneity of the distribution of these fluid components like the carbon does. Of course, the carbon can be present as a solid state. We do know carbonates are important, but the carbon is a very sensitive element so that it can be balanced with the carbonates to form CO2. As we all know, this is the problem we are struggling with right now. So let's consider the carbon right now as a potential source for CO2 as a fluid phase. So we see the presence of atmosphere and going down there, even reaching the core, and we see that it is differently distributed. So there is a heterogeneity in a vertical scale. And of course, there is a heterogeneity in this horizontal scale that we can see in the light of geodynamics, of course. We know that there are a lot of attempts to calculate the bulk carbon concentration at different geodynamic settings, and we can understand that we expect the lowest carbon concentration at middle ocean ridge basalts. In contrast, we see the highest carbon concentration in subcontinental lithospheric mantle part or the deep lithospheric part at cratonic or circumcratonic conditions like the Olduvai and Nyiragongo, which are actually volcanoes at the Eastern African Reef System that Alexander Kopter was discussed about. Okay, so we can see about 20 ppm carbon concentration up here in the Middle Ocean ridge basalt settings. In contrast, we can see about close to 700 ppm, so orders of magnitudes different. Maybe this, what I was just thinking, that maybe this carbon is not only originating from the base of the lithosphere, but also maybe it's a plume-related one. So my idea is to change a little bit the term hydrous plume to carbonic hydrous plume, because we can maybe consider it's not only OH that can be counted on it in the models, but also the carbon is a very, very important component, because what I've just said about this compressibility difference. Okay, so we understand that there are vertical and horizontal differences. Okay, I just got back a little bit. So we are dealing with quite a significant depth up here. It's a very, very thick lithosphere. Okay, why do we care that? We do care, just like, for example, the Olduvai is a recent volcano that produces vast amount of CO2. If we do not get the anthropogenic effect and biologic effect, and we concentrate on the volcanic effect, Olduvai is the highest of their CO2 flux in the geology by means of the geological processes. Extremely high CO2 is added relative to other volcanic processes to the atmosphere. So this CO2 should have been derived from deeper part of the lithosphere, but it's not only that. There are CO2 flux and significant CO2 flux from the base of the lithosphere, from the deeper part of the lithosphere, reaching even surface, reaching even the subsurface level, but we can say that it communicates with the atmosphere. And I just selected a lot of some of papers from out of I don't know how many hundreds. So it's really a fashionable topic right now, how the continental rifting and the carbon emission is associated with each other. With one example, exception, sorry, up here, all the other papers are published in Nature Geoscience. So you can see the titles: massive and prolonged deep carbon emissions associated with continental rifting. Displaced cratonic mantle concentrates deep carbon during continental rifting. Carbon concentration increases with depth of melting in Earth's upper mantle, and potential links between continental rifting and CO2 degassing and climate change through time. So here the climate change comes on the table because there is a process, there is a CO2 leaking process that we still don't know how effective it is by means of CO2 flux, and we have to understand. And we do know that this CO2 derives from the deep lithosphere because of isotopic constraints. Okay, let's take a look at other fluid molecule building elements, which is the nitrogen, of course. The same situation can be said for the nitrogen as well, and nitrogen is also very important. Why? I will let you know, and I will refer to some potential link with earthquakes. Of course, it will be needed more investigation, but I just would like to come up with an idea. Okay, so let's see. You can see a schematic figure up here, how the different geodynamic processes affect the presence of nitrogen in the lithosphere. Of course, there are two major parts of how the nitrogen can be present. It is present in mica, feldspar, or clay minerals as an ammonia molecule up here. Of course, depending on the stability of these minerals and also the oxygen fugacity of the environment. It is very important. And secondly, once we are out of this oxygen fugacity environment, so once the environment is oxidized enough, then nitrogen, a diatomic nitrogen molecule will be liberated. Very typical for subduction zone and very typical for deep lithospheric processes. Okay, so we do know that nitrogen can be incorporated in diamonds, so it can be incorporated in quite deep part of the mantle. And we do know that nitrogen can be very rich in shallower part of the lithosphere relating to organic materials. And of course, we do know the importance of atmospheric nitrogen. But if we consider the mass balance, if we want to count on the nitrogen on the Earth, the planet Earth, then there is something missing. So we can calculate something up here. We can calculate the nitrogen content, what is found in the diamond mainly, but we don't know what's going on up here. So I mean, at the lithospheric mantle depths and lower crustal part, we cannot count enough nitrogen. There should be other nitrogen source whatsoever. Okay, so the problems are on, and now I'd like to give some case studies, what we found in light of this introduction. Well, actually, to be 100% fair, I would invite Tamás here to give the presentation about the first case study, because actually this is his PhD study, and this is the result of his very nice PhD thesis. But Tamás was kind enough to let me to give the most important result of his thesis. I would like to concentrate on the fluids. Okay, so not knowing how the subduction had been initiated, and not knowing whether it's a continental part or it's an oceanic lithospheric part, certainly, if there is a subduction initiated, then this lab that contains minerals will be destabilizing because of the progress of the subduction and because of increasing pressure and temperature that, of course, results in thermodynamic non-equilibrium for many minerals. As a result, what we do know generally is that with different proportions, H2O and CO2 are deliberating, depending whether it's a carbonate or a mica or other phases are the ones that are destabilizing. We do know a lot of things about modeling and many stuff from geological approaches, I mean from rock study approaches. But quite interestingly, we didn't know anything about a very, very nicely exhumed subducted zone, the Carbo-Ortega complex. We know a lot of stuff about geochemistry and whatsoever, and field studies and petrology, but there was no information, even though the significance of these fluids, about the fluid inclusions. So this is what Tamás did. He did a very careful inclusion investigation. And why do we like the inclusion, and what do we want for all the modelers to cooperate with? And I'm sending this message to Alessio as well. These inclusions are the input materials for fluids, okay? So if we want to understand the Gargano area and what could have been the fluid composition down there, then we should look the inclusions. Why? Because they are the direct remnants of fluids directly entrapped in a growing, in this case, metamorphic mineral, which is the garnet, but it doesn't necessarily be a metamorphic phase. Okay, so now getting into the geochemical and petrological detail, we do know by looking at the microscopy, the rocks, the eclogites and granulites, we know that these inclusions are primary. It's very important because we know that they are the traces of subduction fluids down there where the eclogites and the granulites had been for where the subduction happened. These nice, small but strong candidates have been investigated by different analytical techniques like Raman spectroscopy and focused ion beam technique. We did very, very fine sectioning, and we did 3D imaging. Why is it important? Because we have to understand very, very precisely the phase relations within these inclusions. Because of course, these fluids trapped at high temperature and high pressure, and now what we look at is room temperature, and we look at it, yeah, the pressure is defined, yeah, of course, the fluid pressure within the inclusion and the strength of the host mineral. We have to understand very finely the phase association down there. And what we see is not only a fluid phase. What we see is a bunch of phases within this. That's why we call multi-phase inclusions. And we see carbonates, we see pyropyrite, which is a silicate containing H2O in the structure, chloride, this is the same. And also we have the residual fluid. So there are fluids up here, dedicated here. And based on the volume properties and based on the minerals that were being analyzed, by the composition, we understood that the composition of this MFI is equal to the host garnet plus CO2, water, nitrogen, and a little bit of methane. Why is it important? Because we see now a residual fluid of enriched very, very significantly in nitrogen. What happens? The originally CO2 and water-rich fluid that contained not so significant amount of nitrogen, according to our thermodynamic calculations, it had been maximum of 10% more, became extremely nitrogen rich because the H2 and the CO2, as we go on at the retrograde path, so as the temperature and pressure decreases, will certainly react with the garnet, will certainly react with the surrounding rock. Okay, why do we think that it should be reacted? We do believe because we check exhumed bodies. Okay, so now we see granulites, aplogites, and other type of metamorphic rocks that were suffering the subduction process and then went to the surface. Otherwise, we wouldn't have been able to look at them. Okay, so here's what happened according to our observations. So if we see all the process in light of geodynamics, so let's see first the ongoing subduction. There is a garnet that forms under this process. So this is a metamorphic garnet forming when the plate is subducting and is progressively subducting. Okay, here you can see the PT of this formation. And then there is a peak metamorphic condition up there at around between 800 to 900 degrees Celsius and fairly high temperature up to about 1.9 GPa. There is a subduction fluid in flux. Maybe there was some mineral destabilizing. We know that it was in equilibrium with the garnet. So nice, we know the composition, we know the PT. And then if we check the retrograde path, then certainly there is a zone when it should have been reacted with the surrounding rock. I mean, this is the latest stage. This is a very low temperature and pressure condition that we could have checked and we could have expect this reaction. But once there is CO2 and H2O, and this is something we have to also consider when we like to build and refine the geophysical model as well, that this is a dynamic change in fluid composition. Okay, so it's not a steady state stuff. It's dynamically changing according with being equilibrium with the solid. Okay, so maybe this is also something that promotes the earthquakes as well, because of the composition and pressure changes along the geodynamic processes that is always going on, never stopping, of course. And so what we expect and what we say that during exhumation, during this retrograde P and T decreasing process, the fluid should be enriched in nitrogen because nitrogen is there. Nitrogen is there in the mantle fluids as well. But we don't know these processes that enhances the mineral precipitation, but here it should be happening, okay? So I think if we'd like to check the connection of fluids and earthquakes at active margins, I think we should look not only the CO2 and the water, but we should look the nitrogen and the methane. Of course, there will be other challenges because we have to distinguish the atmospheric nitrogen from these nitrogen coming from deep down the earth. But this is a kind of very clear but important lithosphere scale fluid upward movement processes. So here's our message about subduction zone, and those who are interested in the details are always welcome to reach us and Tamás, and highly invited for the PhD defense of Tamás that will be going on in maximum 2 months. But also is highly invited to check these 2 papers that are just freshly out. Okay, and when I got the schedule of this very nice seminar, I was very happy to see that Alexander Koppler was planning to talk about the East African Rift System, because I am lucky enough to be involved in another project that also deals with East African Rift System by means of the significance of fluids and melt formation, and I'm happy that we could somehow relate to each other. Okay, why is it important? Because, and I just forgot to mention it, but I'd like to highlight it now. Because of this vertical and horizontal heterogeneity of fluid components, we can somehow, to some extent, say, once we don't know its origin from a deeper fluid inclusion or melt inclusion, if we check the composition and the density, then we could have at least 2-3 guesses which geodynamic situation it derives from. Nitrogen rich, it could be rather a subduction zone if this reaction took place. And this is very, very valid for magmatic composition for the rift, continental rift system. Why? Because the very special situation of melting, partial melting of thick lithosphere that is very enriched in modally metasomatized components, they are typically silica undersaturated and very, very rich in alkaline components. Okay. We again decided to ask the inclusions, but now they are not only fluid, but melt inclusions, or correctly saying, entrapping melt and fluid phases as well. The rocks we investigated are cumulate rocks. It's a very special type of rocks originating from a deep part of the lithosphere. And what is important to say about them is that they are the very first liquidus phases. In other words, if there is any magmatism, they were the first rock that was being formed during the melt evolution. Okay, and these cumulate rocks entrapped this very, very special type of melt inclusions. We heated and quenched these inclusions, and we could understand that that would have been at about 1100 degrees Celsius, a silicate glass, a carbonatite melt, and a fluid phase. What we do believe is that we got a point just immediately after this immiscibility. I mean, there is a parental melt, but why is it important right now? That we do know that below the East African Rift System, there is a very, very carbonated silicate melt. But that very carbonated silicate melt is being present there, and we have to understand how does it relate to the lithosphere-scale fluid and melt processes. Okay. As I just highlighted, the composition of fluid and melt can be very sensitive to the geodynamic setting. This is quite nicely seen here because such low silica content together with a very high alkali content and it is associated with high calcium content has a hint that this melt relates to the very low degree partial melting of a modally metasomatized thick lithosphere between about 2.5 to 3 GPa at a temperature of 1100 degrees Celsius. So this low degree of partial melting, how can we relate it to geodynamics? We can relate to it that it's representing a very early stage of rifting. Okay, so these are the very first candidate of melts once this kind of thick lithosphere tends to rift. Okay, the first droplets, we can imagine this. And what is important is that once we see these continental rift melt compositions, they are always extremely enriched in CO2. So no matter where you go, we check the GeoRock database and we understood that this is happening all around the world in time and spatially as well. So the CO2 is there in the source. You remember it was the highest carbon concentration. it was the highest concentration actually up here. And this is what is reflected in the melt inclusion as well, because we see, according to the Raman spectroscopic analysis and calculations, that we have the highest dissolved carbonate concentration for the silicate melts. This is extremely high if we got between 5 to 10 weight%. Normally it's up 1 or maximum 2 weight% for a basaltic rocks, but here is extremely high. So this CO2 is being there by 2 reasons. One is it helps this melt formation. And why is it important? We know that these melts can later on, during their later evolution, be immiscible with the silicate melt and the carbonatite melt, as represented by the oldonyolengite. And we do know that these calcite carbonatite rocks are a very good targets for rare earth elements. Actually, the EU had a call to better investigate these kind of rocks because they contain extremely high amount of rare earths potentially. So that's why we need to understand their formation condition and the geodynamic setting behind. And secondly, this high CO2 content of the base of the lithosphere of such, but not necessarily this thick lithosphere, we can have it for the Pannonian basin as well, are the ones that can somehow communicate with the surface. Again, the paper is out about it for the East African Rift System story, so please have it if you are interested. I will say a few words later on, get back to this tectonic degassing, but let's see the concluding remarks. Okay, so first of all, fluids play a fundamental role in plate tectonics, geodynamic processes. It's not something that we have to say just to power the results we are offering here. They do play fundamental role. So we do treat them in a holistic way. We do treat them together with the solid state processes. Fluid properties with special attention to its chemical composition can be characteristic by means of vertical and horizontal scale to its geodynamic setting. Of course, there are lots of things to do just to refine it, but I think we could do it somehow. It's similar than the basalts, the OE basalts and the Moore basalts can a little bit different with each other because they reflecting different situation on the earth. This is true for the fluids, and this will be very helpful for us in the future. As subduction zone, more attention should be made to a nitrogen and methane-rich compositions, besides the famous fluid components like the water and the CO2 do. Of course, we shouldn't neglect them, but we should add the nitrogen and the methane going from deeper parts, more attention when considering the exhumation process. And I'd like to highlight again, the exhumation controlled dynamic fluid compositional change is a powerful approach. So I think this is an approach we should continue and we should move on with. The continental reef setting is one of the best environments to deliberate CO2 from the deep lithosphere by the upward transport of this fluid, as evidenced by 2 processes. One, the extreme CO2 flux related to East African Rift System volcanism, and the high CO2 flux at tectonic degassing sites. The lithosphere-scale fluid degassing exists anyway, distributed throughout on the planet Earth, and needs further investigation because the fluxes between these 2 guys are not known so much, so we have to refine it. And this is what we are going to do. Actually, we are trying to do it in the future for the case of the Central-Pannonian basin, where we see already the traces of CO2 degassing, even though there is an inversion going on, but there had been an extension. But we see this CO2 degassing, and we'd like to understand, due to the support of the Hungarian Academy of Sciences and the Lendület project, and using this fluid inclusion approach that seemed working nicely, how the CO2 can reach the deep part to the atmospheric part. Thank you very much for your attention, and if you're interested in the Lendület project, then please follow our website.
Thank you, Marty. So now after the rocks, we also have the fluids, and not any kind of fluids, but high pressure fluids. I just want to shortly recapture this session because it was very interesting. Eszter first touched on the geothermal energy resources, and Kristóf focused a little bit on geo-hazards, earthquakes, and its connection to the Pannonian basin. And eventually, Márta put that whole thing into a coherent theme, showing that from the depth to the surface there is a continuous process. And also, those who are online and here, it's a very good message that earth science is a very important thing in these days, because we are able to do research both on the geo-hazards and also on the geo-resources. And now this is the time before a short technical break to ask the audience whether there is any question. I see on Cyr that he has one or a comment.
Yeah, very, very interesting presentation, really an eye-opener for many things. Can we go back a few slides to this cross-section? Yeah, this one. Let's say, if you look to this volcanoes and what's below it, basically at first sight it looks like finger-shaped penetration of the lithosphere. Of course, the cases I presented, you have seismic tomography showing this. My question here is there something like that basically imaged by seismic tomography?
No, they are.
Or is this essentially a cartoon? Because it's very interesting. I mean, also whether, let's say, this position of the reservoir, so to say, is accidental at the edge, or whether the keel basically has been affected by this thing. I mean, how well constrained is this? In other words, by observations.
Well, it has nothing to do with the seismic tomography, unfortunately, but it has to do with geochemical data of volcanic rocks together with experimental approaches. So what we did, and actually it's not my stuff, I cited wrongly because the other figures are cited there. It's a paper of IUPA and co-workers in the Nature Geoscience. So what they did, they checked the composition of these volcanic rocks and also the xenolites, the chemical composition, and also checked the results, the melt and the rock relations and fluid relations of experimental works using these chemical inputs and chemical bulk system, and then checked, okay, what we can expect once we want to understand how it's formed, and let's see how it goes at higher pressure and temperature with controlled oxygen fugacity as well. And this is the carbon composition we can expect. And as far as I remember about the error is, yeah, for this, I think it's about 10 orders of 10 ppm, but I think for this, yeah, it can be 100% of error, but still, given its very high carbon content, it's okay. Let's say 700, and then the error is about 20 or 30 ppm. But the point is, maybe we have to refine it in the future. But the point is that relative to each other, here is the one where the CO2 concentrates in light of geodynamics.
If we would see a thing like that in seismic tomography, we would call it the baby plume. Baby plumes have a typical radius of 50 kilometers. What would be here the radius? I mean, based on what you infer from the data you mentioned, what is the typical radius of this thing?
Well, I don't know.
I mean, how small is it? Or is it something that comes a little bit in the neighborhood of what we observe under the Eiffel?
Yeah, well, here the situation, I was a little bit refined the situation, but I didn't want to get into the detail. Here we have this high carbon concentration below the lithosphere, but actually what we can have as a compositional information is rather to the very, very base of the lithosphere itself. It is just a calculation, and because there is a thermal effect, according to the idea of this plume story, and there is a partial melting of the lithosphere, of the modally metasomatized lithosphere, which affects, okay, so what they try to understand, how can we relate to the asthenosphere, the effect of this melting. Okay, so this is a question about lithosphere, asthenosphere boundary stuff.
Okay, thanks.
More question? I'll see. Okay, so you are volunteer for a quick question.
I'm always on the provocative side. No, just to understand better, Martin, Thomas. I didn't get exactly. If you know where this nitrogen, and methane enrichment happened, what was the depth, temperature condition? Maybe you mentioned it, but maybe I skipped it.
Well, this is the point we have to somehow, I get back here. This is the point where we have to somehow differentiate what we got from the inclusion and what we expect for the exhuming rock body. Because we see within the inclusion metastability. Why do we see? Because the petrographic observation by the focused ion beam technique clearly indicated the co-precipitation of solid phases like carbonate, pyrophyllite, fluoride, and so forth. In contrast, what we do see on the thermodynamic calculation that worked well for the chemography and worked well for checking the equilibrium, so worked well for anything else, indicates us that we should have seen first carbonate precipitating, like you see here is the entrapment condition, okay? Being in a perfect equilibrium. See, this is a very lucky situation because normally we don't get the equilibrium, which is normal, but we were lucky enough to get it, okay? And then if we check, no matter which way we go, we consider it as a retrograde path, then we should have crossed the carbonate stability field up here. So first carbonate should have precipitated, and then the pyrophyllite should have been precipitated. What we do see, in contrast, we see a co-precipitation of these minerals by this very distinct pressure and temperature. So within the fluid inclusion, this reaction took place at this quite shallow PT stability field. And the metastability is something that we need to consider, so the kinematic effects and so on, but I'm not getting into the detail right now. The metastability I'd like to highlight for these metamorphic rocks and the inclusions within is common phenomena. We are not the first ones who wrote it. Bruna Carvalho also dealt with it in detail. Once we see, like, for example, quartz and corundum in one inclusion, which is impossible, okay, because they cannot be in they cannot be equilibrated with each other, okay? So this is a metastability story. That's why we just say it's a schematic idea that at around 200 to 400 degrees Celsius, there is a zone where the nitrogen enrichment can take place for the fluids, okay? So it must be, but we don't know how about the metastability for the metamorphic exhumation story. Okay.
If I understood well, that you said that these in fact, affected the whole rock. Or if I understood well.
Yeah. Well, here.
Yeah. In general,
correctly speaking,
in that particular place, that you have entrapped fluid inclusions, it is enriched by nitrogen. And what could be the effect on the host garnet and the host rock in general?
Yeah, well, what we did is that we checked the inclusion garnet system, because once it attracts, then of course there is no communication with the fluids and the rock any longer. Okay, so correctly saying, checking the composition fairly, then we have to check first the fluid and the garnet. But then we check what we did. We used the bulk rock composition and we did the thermodynamic calculation for the bulk eclogites and the fluid we got in equilibrium at the time of entrapment with. And we saw exactly the same with this mineral precipitation modeling using the perplex. We saw exactly the same nitrogen enrichment. Of course, the fluid didn't react necessarily only with the garnet, but other silicates. Okay. Doesn't make so much difference. Okay, there was a little bit difference in the nitrogen enrichment, but there is. Okay, this is the point.
Thanks. Thomas, a very quick one, because we are running a little bit, not a little bit behind the schedule. Just put the blame on me, don't worry.
Okay, just a very quick question. We know that CO2 and H2O affect stabilities of minerals. And we know that, we know this. And to keep it quick, do you expect nitrogen also to destabilize minerals, or you say that it doesn't really affect the stability of the minerals themselves?
Well, actually, according to the experiments of Lee and Kepler, they did this comparative study. Nitrogen does not affect as much the mineral stability as the CO2 and H2O. So once you add CO2 or H2O to the system, then the phase topology can be dramatically different than without CO2 and H2O. But adding nitrogen is rather an inert phase by means of mineral stability. Okay.
Yeah, thanks.
I just ask the online participants as well if there's Chongi can, because I'm a little bit IT bushman, so I'm not sure that I can find out. Okay, no question. That's good. So Marty, thank you so much. We are closing now, also telling this to the online participants that we are closing the second session, and we will have a technical break. And just checking the time. Oh, well, I'm also asking the online on-site participants, sorry, is that okay if we reconvene at 3:15, 15 minutes? And I also make an announcement in the chat window, those who haven't joined yet the online meeting, that we are starting the third and the last session at 3:15, okay? And we try to be more on time, but we had very lovely discussions, so I think we shouldn't save this time. Thanks.